الرحمن الرحيم. راح نبدأ اليوم محاضرة تتكلم عن السامبلينج ثيوري. اوكي، حتى نتكلم عن السامبلينج ثيوري راح ناخذ continuous time signal ونعملها سامبلينج وندرس الاثر السامبلينج على هذه السيجنال اللي راح نشوفها احنا وياكم. عشان هيك without loss of generality we'll take a cosine signal في حالتنا تبعتنا في اليوم هذا. Okay, so let's take a continuous time signal نعتبرها XA of t equals a cosine omega 0 t plus phi. So this is our signal. This is a continuous signal. We have t, x of t, and a here is for analog or continuous. It's the same. Here we have omega 0 that represents the continuous time angular frequency. Angular frequency ووحدتها راح تكون في الراديانز بير سكند حسب ما بنعرف. راح نشوف احنا لما بننتج السيجنال راح تنتج عندنا فريكونسي اخرى بس راح تكون discrete time angular frequency، راح تكون وحدتها radians per sample. راح نشوف هذا الحكي كمان شوي احنا وياكم. Okay, so we would like to sample this signal at Tn or T sub n instance, where this T sub n is equal to n times capital T, which is equal also to n over f sub t, which is also equal to 2 pi n over omega sub t, where t is the sampling period, fs or ft, sorry, which is equal to 1 over t, is equal to the sampling frequency by the way. The sampling period is in seconds. This one is in hertz, which is second inverse, and omega t, which is equal to 2 pi f sub t, is the sampling frequency but in radians per second. Radians per second, okay? Okay. Now, to do the sampling, we will go to the time domain signal and we will apply this at those discrete instances. T equals nt. So we will have a cosine omega 0 in capital T plus phi. Now, this can be written as just arrangement of the variables inside. So this cosine omega 0 times t times n plus phi. I will call this to be equal to a cosine omega 0 n plus phi, which is equals to x of n. So what we have here is the discrete, this one here is the discrete time signal. So a cosine omega 0 n plus phi is a discrete time signal, and it's a function of the index n. It's not a function of, actually it's hidden a function of time, but at discrete instance of time. And here is the relationship between the discrete time frequency and the continuous time frequency. So omega 0 is the discrete time angular frequency, and its unit is radians per sample. It's not radians per second anymore. And this is what we actually got. So whenever we need to do the sampling, all what we have to do is to come with the frequency, the analog frequency, multiply it by the sampling period, and you will get the discrete time frequency. Okay. Notice, by the way, that we took the analog signal as cosine signal, but this also can be applied to any signal, taking into account that any signal could contain many frequencies inside. So all those frequencies will be changed by this one, and we will get the discrete time signal. Okay. I'm going to take an example and see what will happen. So we'll have an example. Consider three continuous time signals. G1 of t equals to cosine 6 pi t, and it has one single frequency, cosine, a single frequency, and this frequency f1 equals to 3 hertz. Okay, we know that the frequency in radians per second, it's 2 pi f, so 2 pi f is 6 pi. Okay, so this one here is omega 1, which is equal to 2 pi f1. So this relationship, 3 times 2 pi is equal to 6 pi. Okay, G2 of t is equal to cosine of 14 pi t. This means that we have f2 equals 7 hertz. Again, G2, we have omega 2 equals 2 pi f2. Okay? 2 pi of 2, 7 times 2 pi, it's 14 pi t. This is the number here, 14 pi t. Okay, G3 of t is also one single frequency, and it's equal to cosine 26 pi t. And here f3 is equal to 13 hertz. So we have 3 frequencies. One of them is 3 hertz, the other one is 7 hertz, the third one is 13 hertz. The 3 signals were sampled at a rate, at a sampling rate of 10 Hertz. Find G1 of n, G2 of n, and G3 of n. So we need to sample those three continuous time signals, get the discrete time respective signals that corresponds to each one of them. Okay, so to do this, we have t equals 1 over ft, and this equals 1 over 10, and this is equals to 0.1 second. So our sampling period is equal to 0.1 second, which means that in 1 second you will get 10 samples. This is what we have here. So our sampling rate is 10 samples per second, or the sampling period is equal to 0.1. So if we apply this through this rule, omega 0 for the first one, omega 1 is 6 pi times 0.1, so it's equal to 0.6 pi. So G1 of n is equal to cosine 0.6 pi n. 0.6 pi n. So this is my G1 of n. G2 of n equals to cosine omega 2 is 14 pi radians per second times 0.1, so we will get 1.4 pi n, and it's 1.4 radians per sample. And actually, it has exactly the meaning. You know, when you say you have 1.4 pi n, this means that between two successive samples, you have 1.4 pi radians. So 1.4 pi radians is between successive samples, the period between successive samples, if you are taking the x-axis to be in radians. Okay. Now, I'm going to look at G2 in a different way. I'm going to look at G2 of n to be equal to cosine. This 1.4 pi n is 2 pi n minus 0.6 pi n. That's right. 2 pi n minus 0.6 pi n is equal to 1.4 pi n. Okay, now this is the difference between the cosine of the difference of an angles, difference of angles. So this is cosine 2 pi n, cosine 0.6 pi n. You have a minus sign, so you have a plus here. Plus sine 2 pi n sine 0.6 pi n. Now, cosine 2 pi n is equal to 1, sine 2 pi n is equal to 0. So the answer here is cosine 0.6 pi n, which is equal to G1 of n. So two totally different, completely different signals in time domain. When you sample both of them at this rate, which is 0.1 second for each sample, you will get G1 of n and G2 of n to be exactly the same. Okay? Okay, let's look at the last one. So G3 of n is also equal to sampling this one, 26 pi n multiplied by 0.1, so you'll have cosine 2.6 pi n. Okay, 2.6 pi n is also can be written as a sum of two angles, cosine 2 pi n plus 0.6 pi n, and then we will distribute the cosine. So you have a cosine 2 pi n cosine 0.6 pi n minus sine 2 pi n times sine 0.6 pi n. So multiplication of those two, this one here is 1, this one here is 0, so you end up with cosine 0.6 pi n, which is equal also to g1 of n. So the three signals happen to be, when they sampled, happen to be coincide with each other. Their samples are coincide with each other, and they are on top of each other, and this means that they are equal. So the three sequences are identical. So they are identical. Actually, all cosine waveforms of frequencies given by 10k plus or minus 3 with k is any non-negative integer gives the same answer as above. I mean here, when you get 3, actually you got k equals 1, it's 10 minus 3, 7. You got also 10 plus 3, 13. If you take k equals 2, so you have 20 plus or minus 3 is also the same. You also have 30 plus or minus 3 is the same. And so you will get all those frequencies will give you g1 of n, which is here. The reason why is this. Notice that if you still remember from communication courses, there is something called the Nyquist rate. The Nyquist rate states that if you want to do sampling and you don't have to get aliasing, then you have to do the sampling frequency to be ft is greater than or equal twice f maximum. So your sampling frequency should be more or equal to twice the maximum frequency in the signal. F maximum is the maximum frequency in the signal. So if you want to do sampling, you have to be careful about this. Notice here that we are sampling at 10 hertz. The 3 times 2, this is the maximum frequency in this signal because it's the single frequency actually. 3 times 2 is 6. This 10 is greater than this one, so there is no problem. This one is 7 times 2, 14. It's greater than this one, so aliasing will happen. And 13 times 2 is 26, is also greater than this one, so aliasing will happen. Okay, let's see this from a frequency perspective point of view. Let me erase this and come back to the signals and do the spectrums of the discrete time sequences. Notice that with some to some multiplicative constant, if we take G1 of t and see the spectrum of G1 of t, spectrum of G1 of t, which is G1 of f, you will have two arrows, one of them at -3 hertz, -3 hertz, and this one at +3 hertz. Don't worry about the amplitude at the time being, just notice the location of the spectrums. So you have an impulse at +3, another impulse at -3. This is done by doing the Fourier transform of the G1 of t. Now, when you do sampling, what will happen to this spectrum? This spectrum will be repeated at 0, at fs, twice fs, or ft, which is the sampling frequency. So G1 will be like this. If this is my 0, so this is the spectrum of G1 of n. What will happen here is that we will have an arrow, an impulse at +3, -3. Now, we will also have at 10, so this spectrum will be repeated around multiples of the sampling frequency. The sampling frequency is 10 hertz, so you will have this one at +3, so at 13, and you have one below, so at 7. Okay? And at 20, you will have exactly the same. So you will have here at 23 spectrum and at 17. So the spectrum repeats itself, and this one goes also. Let's take another, so just to be more accurate. So I'll take 30, so you'll have at 27, and you'll have at 33. And from the negative side, it's the same. So we'll go here to -10, and this is -20 and -30. So you'll have at -7, -13, -17, -23, and here also we'll have at -33, -27. And it continues on. This is the actual spectrum. The actual spectrum is this one here. These are repeated because of the sampling process. The sampling process repeats the original spectrum of the signal so many times around the sampling frequency. The sampling frequency here is 10 hertz, and those are multiples of the sampling frequency. Let's see the spectrum of G2. So I'm gonna draw the spectrum of G2 of n. So we will have the original spectrum of G2 here. This is the spectrum of G2 of t. So you have one impulse at 7 hertz and another impulse at -7 hertz. So this is how the spectrum of G2 of t looks like. G2 of n is a sampled version of this one. So this spectrum will be repeated around 10 hertz. So for the first one, it will be at 7 and at -7. Okay? Now, when we go to the sampling frequency, 10, we will go down by 7. If we go down by 7, then you are at 3. So you have a spectrum of 3. And you go up by 7, so you are at 17. Now, if you go to -10, you will go down by 7, so you are at -3. And you go down also by 7, so you are at -17. Okay. So at -17. Okay, go up to 20, twice the sampling frequency, and you go down by 7, so you are at 13. You go up by 7, so you are at 27. Okay? If you go to 30, so you go down by 7, you are at 23. If you go up by 7, you are at 37. Okay? Now you go down, -10, you have those two, -20. So you go down, you are at -13. You go up, you are at -27. If you go to 30, -30, sorry. If you go to -30, then you are at -23 and at -37, somewhere here. And we continue here, and you continue there. If you look at the two spectrums, they are exactly the same. Those two spectrums are the same. We found that G1 of n and G2 of n are the same in time domain, discrete time domain, and definitely their spectrum, actually, they are also identical. So you have identical spectrums. Please do the spectrum of G3 of n yourself. Okay? Do it and make sure it is identical to that of G1 of n and G2 of n. Notice how aliasing happened when you have 7 and -7, that when you sample it at 10, it goes down, and now it looks like as if you have this is your original signal or original spectrum. So this one and this one is the same, although you have a spectrum of G2 to be at 7 and -7. This happened because your frequency here, the frequency of the signal is 7 hertz, and Ft equals 10 hertz. So Ft actually is lower than twice the F maximum, which is equal 2 times 7 and equals 40. Okay, and this Ft is 10 hertz. Okay, I hope by this we can understand what happened in sampling, what will happen in sampling to the signal, to the spectrum, and we got a little bit about the a little bit of information about the aliasing, and now you can understand more what is the aliasing and how it happened and how it is you can get different signal from the original one if you do the sampling with a frequency that is lower than twice the maximum frequency in the signal. Thank you very much, and I hope this is a good lecture for you. Thank you.